any specific questions before we start? Alright, we'll start off with the basics. The first module, as I mentioned, tools first. We'll look at all the tools that we need to use for development. We'll use a few of the tools hands-on here. And then we'll look at the APIs, various types of APIs of Unix, POSIX family, the BSD family, and system file family. So today's session is again basics. The whole of first module actually is about the basics. So in case you have any question, you can put up your hand and interrupt me. I'll answer your questions. We'll begin with a tool chain called GCC, or the GNU Compiler Collection. Because throughout this particular course, we'll be using GCC as a primary tool chain for compiling the binaries, for compiling the sources and generating the binaries. We'll be using initially this particular tool chain as a host compiler for the first module. The second module, we'll be using this to build our kernel drivers. Third module, we'll be using this as a cross tool chain to compile the binaries for ARM or PowerPC targets. So throughout this course, in all the three modules, we will be using the GNU Compiler toolchain as a primary toolchain. We'll get acquainted with this. We'll get to know what components are there in GCC or GNU Compiler Collection and what each component actually does. So the first session is about getting to know this toolchain. Before we start, if anyone is completely new to Linux, there are two ways to get help for a machine from a Linux box. One is to use man. Man shows you man pages. You can access the man pages for functions. Say for instance, library functions arguments or library functions specific overview if you want to look at. Man space function name will give you access to man page of that particular function, which talks about the usage. Similarly, you can access man pages of APIs. Similarly, you can access man pages for tools, various tools that you may have to use like debuggers, compilers, profilers, the optimization tools. Whatever tools you are using, you can access the man pages of those tools. So the primary usage is man space the tool name, function name, or API name. Man pages are organized into various categories. We call them as sections. So it will bring the appropriate man page depending on what you have mentioned from an appropriate section. We'll get to know more about the details of section as we move on. So here, man space GCC gives you a little overview of GNU Compiler Collection, description of how it is built, and various flags it accepts. We don't have to read the entire man page if you're a beginner, but just know that man pages exist. In case you're confused with any flag, you can look up for help here. Right. So this is the first tool. On few machines you'll also have, especially Fedora distributions, you'll have one more tool called info. Man is one way to get help, info is the other way to get help. Ubuntu kind of distributions, I'm not sure if info directly is available, you may have to install it explicitly. But in case of Fedora, you may find info. The difference between info and man, man usually talks a lot about usage, which means that if you are aware already about why this tool is designed, what purpose it serves, if you want to know more about various options like various flags, you can access them from man. But info gives you a complete manual, a complete ebook on that particular tool, which starts with overview, the purpose, why it is designed, and then goes into usage. So man is good for reference, info is good for knowing about the tools. In this case, I've not got the info, so it opens up the man page. In case of Fedora, you'll find info. If you want to install info on Ubuntu kind of distributions, you will have to install an external package. So these are two ways to get help. Quickly we'll run through some tools, some commands to get acquainted with GCC. So GCC is a GNU Compiler Collection. This particular compiler collection can be configured to be used with an IDE, like an Eclipse IDE or some other IDE. Or this particular compiler collection can be used directly on the command line. By mentioning its name on the command line with the appropriate flags, you can initiate the compile operations or build operations using this particular collection of tools. What we'll be doing now, we'll be looking at a simple C source. We'll try and compile that particular C source into an binary and then try to execute it. For the beginners, these commands are important. If anyone is beginning with Linux, these are important commands. So based on your backgrounds, you can decide whether to take down the particular command or not. Before we start off, it's a simple C source. There's nothing much there. A simple .c file with one main function with some printf call. So what I intend to do with this is I intend to compile this and build an application out of this using that compiler collection called GCC. Let's take a look at how it is done. So it is done like this. We have 4 different tools within that component called GCC. GCC basically is an integration of these 4 tools. There are 4 different components. One is called a preprocessor, the other one is called compiler proper, the other one is called assembler, and then linker. These 4 tools combined, integrated together, makes up the GCC. So when you present a source file and you initiate a compile and build operation, GCC internally invokes these 4 tools, one after the other. Each of these tools is pre-configured to take up one type of operation. Preprocessor resolves all the preprocessor directives. Compiler translates your source into assembly equivalent, depending on the machine. And assembler tries to translate all that assembly source into machine equivalent. And then linker applies a process called build to create an executable binary that can load and run. So we'll just take a look at how to use or how to access these tools. Both the ways, if you are writing it down, if you're a beginner, quickly you can finish. On the extreme right, you find the source file names. On that side, onto my left, you'll find the stages involved. The source, preprocessor, assembly, relocatable, and then executable. People working on Linux platform, you could be familiar with these basics. So you need to bear with me for the next 1 week. After a week, maybe some interesting sessions for you, those who are familiar with all this. Let's try now to initiate this process. We'll try and invoke one by one each of those tools and initiate this. Our objective actually is not to verify that source file. Our objective is to know how these components can be accessed independently and how we can verify the outputs of each of them, so that if at all we are to troubleshoot any of the compile time problems or build time problems, we can look at the log dump and then verify where things have gone wrong. So it's just to know the tools and their usage. So we'll stop at each of these stages. We'll try and apply the process step by step. Watch this. So I've got the source file 1.c. Generally, we do this. But this is one of the options. We say we present the source file there. -o is a flag that indicates the output where it is to be redirected. We are redirecting the output, which is the binary code, into a file called 1. If you don't choose a file, say for instance you don't choose an output file, the default output file, default binary file created in Unix platforms will be a.out. A.out has been a practice since a.out was a binary format. Now a.out is no longer a binary format, but still that practice is on of choosing the default name as a.out. So that is a single shot, a single command if you want to initiate all that process. Then you can do it this way. But our objective is to do it step by step so that we understand these components. So let's get started. We'll do step by step. First step is to run the preprocessor. This is the flag -uppercase. Linux command line commands are case sensitive, unlike Windows. So uppercase E. Uppercase E will take that 1.c, initiate the pre-processing, and then after pre-processing is done, you'll have the output dumped into 1.i. So now we are initiating the first step of the process. You've seen the source code. In my source code, I have one stdio included, the standard C header file included. You could see this, and I've got a main function with a printf call. So after this is done, you can see simple, all the preprocessor stuff is resolved. You can see a lot of code added. It means whatever was there in that stdio is extracted and appended to your source. By the time compiler sees your source, the code that you wrote is there on top, all that code that was extracted and appended from the header file. It means by the time the compiler views your code, there is no longer a header file. Header file has been resolved, isn't it? There is no such component called header file by the time compiler looks at your code. So all this has been. Now let's take a look at one more flag. There is a flag called -v. Most of the tools in Linux and Unix domain, they accept this flag -v. Usually they support this flag -v. -v is referred to as verbose mode. When you run a particular tool in the verbose mode, it will show you what it is doing at the back, the steps it is executing at the back, the configuration steps it's executing at the back to achieve the objective. The objective here that we are presenting to GCC is to take that source file 1.c, apply preprocessing on it by invoking the preprocessor. So -v will now show us what GCC does to do this. So watch this. This is the log generated. As developers, sometimes we will have to look at these logs to know some issues. So if you look at what GCC is doing to carry out this job, it is first trying to read in some file, some specification file called specs. It means when compilers are installed, when the host compiler is installed, in some predetermined directory, a specification file is stored. So it is now accessing that particular built-in specs file, and then it is trying to verify the compiler chosen, and then it's trying to know which target platform the process is to be executed for, the processor type and the kernel type or the operating system. And then it's trying to verify whether all the required dependent tools or dependent libraries exist or not. Because the preprocessor itself is a binary, isn't it? Preprocessor is a tool. That particular preprocessor could be compiled or could be using some libraries as part of its source. So all the required dependencies should be there. It's trying to verify if all the required dependencies exist. And then it's trying to invoke that particular preprocessor here. It's passing the options we have passed, plus it's passing few more options to it. And then the end job is to take this source file and generate a .i equivalent containing preprocessed code. And then you also see a log that talks about where it is looking for header files. You can see this, the header files that you're including in your source code. Preprocessor is trying to look for the header files in those folders. So those are the locations where the header files are looked up for. If the header that you're including is not in that location, immediately you get an error at the compile time, the header file is not found. So like these few things you will know if you look at these logs, and you can troubleshoot the primary problems. So this is step one. Step one, what we have done, we have taken the source, we have invoked the preprocessor, we have generated the preprocessed code. The output confirms that the header file has been resolved. Whatever was in the header file has been extracted, appended to our source code. Now let's go to step two. If you look at that diagram that you've seen earlier, the step 2 is about invoking compiler. And then presenting the compiler the code which was generated by preprocessor. Compiler will now apply the compiled job, that is translation job, and translate those source instructions into assembly. Let's see how it is done. So it is -s, uppercase again, -s. Now this will do the job of invoking the compiler, presenting the compiler with the input file, which is the 1.i here, and then the output obviously is the assembly equivalent. We're trying to store that into a file with extension .s. These extensions of the output files are simply standard practices There's no rule that it should be always 1.s or .s. You can store the assembly output code into .a file, .b file. It is simply a good practice to follow the standard convention, so we are using .s as an extension to identify the assembly source file. So this does the job. This will generate 1.s. Watch this. This is the assembly output code emitted by the compiler. So you have the code for that function main. So main function has been translated fully into assembly instructions as per the processor type chosen. We have chosen x86 as an architecture tool chain, so these are the instructions of x86 32-bit architecture. So we have the compiler version also. We have also got the platform version for which this is being carried out. Quickly run through -v for this also. You'll find a similar tab that you found earlier, but this time it's the compiler being called. You can see the version of the compiler used. You can always know which compiler has been used to build that particular executable by looking at that particular log. So compiler version you can verify there. The compiler has done this. It has taken the .i file. It has generated a file called .s. Right. The compiler is this again. It means this particular tool CC is an integration of preprocessor and compiler. So for both the purposes, same tool is being invoked. So this is step number 2. Let's go to step number 3. Step 3 is about invoking assembler and then translating this code into further machine code. Again, the flag this time has changed. The flag this time is -c, but it's a small case C, it's not uppercase. The first two flags were uppercase, -e was uppercase, -s was uppercase. But this one is a lowercase flag, -c. This will take that particular .s file. Can we give this input the source file .c? Will it work then? It should, isn't it? So any of the previous version of the code you can pass. My input file can be .c also, -c, .c, and then .o. It means we're carrying out 3 steps at a time. Right? So input file can be any of the previous versions of your code. So this will now generate. We call this as object file in Windows platform. Generally they're called as object files because they carry the binary instructions in it. They carry the machine instructions in it. Object files on Windows platform usually have an extension OBJ. The Linux platform will have an extension .o. So .o are object files. Let's again confirm this with -v. We should now find the assembler used. GCC should invoke the assembler. So you can see the log and confirm. Look at this. Assembler has been used. And you can see they're also mentioning about the version of the platform, GCC version and all that, but assembler has been used. The tool is called AS. So assembler has done this job. So now we have a file called 1.o, an object file, which contains that particular code that we have seen earlier. So now watch this. For beginners, this is an extremely important tool that we'll be using throughout the course. At different levels we'll be using this. I'm just introducing it right now. GNU family of tools contains one tool called ObjectUp. ObjectUp is a binary disassembler. This particular tool allows you to watch the binary files. Editors, the text editor like VI or Notepad or OnePad, they will not be able to open and read an object file. They're not designed to view or show up the binary instructions. So ObjectUp is a tool that's widely used by open source developers. There are many tools in this family, but ObjectUp is widely used. And ObjectUp shows you the contents of the binary files. Which means if you want to study about the address spaces, if you want to study about data segments, code segments, or if you are to debug an application using its crash log without using any of the tools, this is the only way to go about it. You have to use this particular tool, ObjectUp, put your crash log aside and then do a reverse engineering. We'll be touching on these aspects as we go on, but ObjectUp is a very powerful, very useful method of debugging. So I'm just trying to introduce that now. This is a tool that will now show us the contents of that file 1.0. 1.0 should have the machine equivalent instructions for the source code that we wrote. So watch this. On top you could see disassembly of section text. We'll talk about what that text means. And then bottom you could see disassembly of section read-only data .ro data. It means your code has been compiled, machine instructions have been generated, they have been logically organized in the file. All the instructions have gone into one section called text. Instructions, we mean what all you wrote in the main function. All the data that you have declared, like constants. In printf, I've passed a string constant as an argument. Welcome to Linux world or something, isn't it? That has gone into read-only data because that is a constant, isn't it? If I have declared any global data, it would have gone into one more category, one more logical section called data section. So you could see clearly the object file is organized into logical sections, and you could read the contents of these logical sections using tools like ObjectUp, and ObjectUp is widely used for that. So you could see there's some additional information called comment, and there's frame information, and that's all it ends there. It means it has the function main that you implemented in the source code. Along with the main function, read-only data is being represented because that was there in the code that we have presented. And then the data section is missing here because there's no global data declared in our code. So this is what you could do with ObjectUp. Again, you could open the man pages for each of these because I'm just showing you one or two flags as of now, depending on the context in which we're talking about the tool. As we move on and use this tool, we'll be using different flags. To know more about all the flags or to know more about the flag description, look at the man pages. It's man space ObjectUp. Here we completed the first three steps. The last step is still remained. The last step is about taking this object file, applying a process called BuildOver it, and generating one executable image. Let's see how that is done. It means we need to use a component called linker. That linker component will have to carry out this process called build process. Let's see how it is done. Watch this. I'll change it for better, easy understanding. I'll call the executable as app. So the output file now is app, no flag here. By default, GCC space and relocatable invokes the linker. So this will invoke the linker and generate the application. So we have the application binary now with the name app. Earlier we had the relocatable on the object file with the name 1.0. Let's take a look at all of them now. This is what we had initially. So we first did step 1, step 2, step 3, and then the executable file. I think app was used, so app. So these are 4 phases, 4 steps. Now as a developer, this is useful because sometimes you may have to optimize the code for space or for speed reasons. Compilers come pre-configured with the optimization settings, but still if you have to optimize, then you may have to look at the assembly code generated for your source. That's how you know how far the compiler is doing the job, because compiler is generating the assembly equivalent source, isn't it? So if you have a look at the .s file, you'll know how your source is being translated to assembly, and if any further optimization is required, any changes are required, you could carry out manually. So optimization, this will help. This will also help look into details of how the addresses are being generated for each of your instructions or data. The compile time addresses, the offsets are being generated. This also helps looking through the object dumps and looking through the object file contents will give a lot of understanding of address space, will give you understanding of how to read the crash logs and debug the applications using crash logs. So this is a very useful tool chain. Up to here, any questions?
Our application file is 1.c. Why it has been changed to ABP?
That's the executable. 1.c is a source code. Your source code is .c, isn't it? How do you execute an application? Do you execute source code? We execute the binary system. So we've carried out the compiling to create a binary.
You can compile directly GCC source code that works.
You can compile. Our objective was not to compile and build. Our objective was to know how it is done step by step. So that if required, you can halt at any step and observe your changes. Our objective is not to compile, run, check functionality. If anyone is learning programming, he will do that. Our objective is to know what tools are doing internally.
That